Can I start here?
Good afternoon, everybody. So today we're going to have the Lucia's presentation in pandemic dark matter. So let's see what Lucia have to say to us.
Thank you very much, Andres. Today we talk about a paper that I will base my project during the sandwich period in Norway. Sorry. So this is a mechanism in order to produce dark matter and achieve the correct relic abundance that is observed. So this mechanism is called dark matter from the exponential growth, also called pandemic dark matter, and was proposed for those scientists here. And here we have the link if you want more details. So, sorry. So this is the how it looks. The first page. In order to, if you can see. They are proposing a novel mechanism in order to produce dark matter from a thermal bath, so I will explore this during the presentation. So, as you know, dark matter relic density is calculated from many observations, and we have this, that is 0.12. And here we have, of course, that the abundance of the dark matter in the universe is about of 27% of the total content. So in order to achieve this, it is difficult because there are many mechanisms that are proposing how to produce this dark matter. So in this mechanism, we have some that are the ones that are based in the thermal equilibrium. Thermal equilibrium is basically when the rate of the interaction between particles can be maintained in some way and can maintain the abundance and the energy distributed thermatically. And this can be achieved since the interaction rate is bigger than the rate of the expansion of the universe. So there are many mechanisms that use this kind of thermal equilibrium. This is the most known of them. This one is the freeze out, the forbidden dark matter, cannibal, zombie, and so on. But there is also other mechanisms that they are not using this, and they doesn't reach the thermal equilibrium at all. In this case, we are interested in the freezing. The freezing is basically that the dark matter was never in equilibrium with the health bath in the universe, in the early universe. And of course, the interactions with the other part of the other content of the universe is very weak. So they don't have time in order to reach the equilibrium, thermal equilibrium, and they will kind of accumulate the production, even if the interaction is weak, in order to achieve the correct abundance, that is the abundance I showed in the previous slide. So, what is proposed here? Basically, is the mechanism that is called pandemic dark matter, where they are assuming that dark matter particle can transfer a heat bath particle into a dark matter particle, as is shown here in this kind of Feynman diagram. The evolution of the dark matter number density in this case is described, of course, by the Boltzmann equation that is given by this. Here, the first sigma b, that is the thermal cross section, is for this process. With, of course, we have the interaction between dark matter particle producing two particles of dark matter, and here we have the opposite case in the annihilation of dark matter producing dark matter in a thermal bath. So, of course, this is the parameter of Hubble. We have here, for example, the number density of the heat bath in equilibrium, and in this case, this will be the number density for the dark matter. So, the solution of this equation is given by this equation there, where we have the epsilon, and here we are assuming an abundance. How it was generated, we don't know. We are just assuming there is a kind of dark matter abundance, a small quantity, and in some way will grow. And this is based on a very known mathematical model that is used in order to predict how will be the rate of expansion, for example, for a virus. The author says that he was inspired during the pandemic to create or formulate these mechanisms. So here we are assuming an initial dark matter, initial quantity, and of course here we have this P that will be like kind of the rate of the generation of this dark matter, governed by this equation here, that of course depends of the sigma V, that in this case sigma V will be the first one, in this case in the production of dark matter, of the interaction with the dark matter and the health bath, and of course this H linear, I don't know how to say that in English. We have the Hubble rate, and here we have this GFFT, that is the degrees of freedom, and here we have the T, that is the temperature we are storing there. So in order to the growth be achieved, we need that this P that was located here needs to be necessarily bigger than 0, because of course if we don't have this parameter, for example 0, we don't grow and we not achieve the correct Rayleigh density. So in order, we are assuming here is in the first step, we have highly relativistic headbath particles, and that can be achieved by this equation here, where here we have this x psi. This x psi is basically the mass of the thermal bath over the temperature. And here this k, for example, when it's bigger than 1, here they are assuming, for example, an infrared dominated transformation processes. And in order to, of course, we know that the universe is expanding. So in some way, in some moment, the headbath particle will become in non-relativistic particles. So in order to describe this, we have this equation that is the final solution of the Boltzmann equation given by this. And yeah, here we are assuming exactly the same one. Here is a kind of the time that is given by, of course, the mass of the over the temperature. And here this sigma, I just forgot what it was, but basically it's a coupling between the dark matter particles and the thermal headbath. Here we have a plot where they are describing this. So they are here, they have fixed the mass of the dark matter in order just to illustrate how is the behavior of these mechanisms. Here they are just assuming the dark matter particle is 1 GeV, and here we have the kind of relation between the mass of the psi over the mass of the dark matter, and is in order of 2. So of course, here they are using different couplings in order to see how will be the behavior of the curves. And here they are assuming these trees, and here they are assuming how will be how is called this like they are using here the rate of the exponential. So they are just saying from the coupling they have chosen there, they can see, for example, how will be the rate in versus the time they are studying in this case. So as you can see, you can situate here in 10 to the 0 that it will be 1 when the mass of the thermal bath will be the equal one to the temperature. They can see a kind of bump here. And this origin, and now it is discussed how will be the origin of this abundance we are using in this equation, because as you remember, we are using this one, but we don't know, we are not very sure how it was produced. So they are using two scenarios. The first one there is using that the time is much earlier than the time of the interaction between the dark matter and the psi. So in this case, they can separate the phases. For example, we have just the production of the dark matter. After that, the production of dark matter, there is a very separate line, and you can start for the exponential growth. And after that, the exponential growth is not maintained because the expansion of the universe. And after that, the relic density is just constant. This could be achieved from the different scenarios, different mechanisms. For example, the UV-dominated freezing. For example, the direct production from the decay of inflaton or heavy particles. For example, they are using the phase vacuum after phase transition, or even with evaporation of black holes. They are using another, they are just mentioning, they don't go through this, but they told that it could be also from some exotical mechanisms in order to produce this small quantity. And they have also a second scenario where we cannot distinguish the line that separates these both phases between the dark matter production and the exponential growth. So they are saying that maybe those processes can happen at the same time and they are related. So in order to show or illustrate how is this, they have applied this in order in this case for the freezing, because in this case is the most interesting one in the second scenario. And in this case, of course, the Boltzmann equation will be transformed. And here, of course, we have the sigma v, as I mentioned before, and the number density in equilibrium for the thermal bath, of course. And here they are, this is interesting in this case because it is produced a small quantity of dark matter. And of course, you can explain the growth of the dark matter in order to achieve the relic density by using this mechanism. So in this case, this is very favorable in order to use this mechanism of exponential growth or pandemic dark matter. So in this case, it's almost guaranteed that the quantity of dark matter, because a kind of lambda that will be the coupling between, even is very weak, if it is very weak, the coupling will exist between the dark matter, of course, and the heat bath. And here, in order to be this and to reproduce the correct result, it is necessary that in this case, this thermal cross-section is bigger than the cross-section that produce these ones. Of course, because you cannot, you never will produce the enough dark matter if this rate is bigger than this one, because you are here producing, in this case, for example, in between the psi more particles of psi and dark matter, and it will never be in equilibrium in the flattened curve that we need in order to reproduce the abundance. So this is a condition we need here. Here they have shown the evolution of the of using different couplings. In this case, will be the coupling of this interaction, psi, dark matter, dark matter, dark matter. In this one, this final one is the coupling for those processes here. Both is for two to two processes. And they have separated the different scenarios with colors. For example, in this case, for example, for the region green, they are using freeze-in. In the red region, they are using freeze-out, of course. Here in blue, they are using freeze-in and freeze-out in the yellow region. In order to produce, in this case, it is important to say that in the green one, in the red one, they are using this interaction here, because you cannot in some way show all the interactions into one plot. So they are using this one, side producing dark matter, for this one green and the red one. And for the yellow and for the blue, they are using, in this case, this scenario, where they're producing of course, the dark matter here in this trace one. And here is a kind of area that is excluded, is already excluded by the VBN. When the mass of the psi is smaller than the 0.5 MeV. And yeah, so basically this is a kind of, they are showing the different situations depending of the couplings they are using for the different process that will generate the dark matter particles. In this case, in the part of blue, the light blue here, the values of this one could not be bigger, because if they are bigger, they will require masses bigger than 140 TeV, and in this case it will violate in some way the thermal cross section we are using here. So here they are using one application for this mechanism of exponential growth. Sorry, I will drink water. And in order to see a real application, they are using a real scalar for the thermal bath, and this scalar will couple to the standard model by using this coupling, quartic couplings of the Higgs portal. In this case, they just obtain this plot here, where you can see, of course, the lambda of the interaction between thermal bath and dark matter, producing two particles of dark matter in this case, and this versus the mass of dark matter in GeV. Here, of course, you can see the different. Here in the orange, you can see what you expect from the spectrum of CMV. Here in green, you will see, in this case, that the phase where the freezing mechanism will produce the dark matter density that we need in the first step, and after that, the exponential growth that will in some way reproduce the current relic density. So basically, this is a very short paper. So basically, the conclusion is this mechanism is a kind of interpolation between the freeze-in and freeze-out, and you can calculate the many constraints from the indirect detection, direct detection, that this have not been done, and I will do that there in Norway. This is very highly predictive, because and it's very controlled in some way, because after the expansion of the universe will in some way finalize the interaction rates, and of course we will maintain the rate density that we need. So it's achievable, and of course this is depending on the initial conditions we are using. Of course, in order to avoid many constraints, it's normal to use in this kind of model the thermal bath. And yeah, and that's all. This is a very new mechanism that we will explore in the future. That's all. This is not done kind of a very big study for other particles such as vector. This is just make for the scalar. But yeah, that's all. Thank you.
Okay, let's thank Lucia for her presentation. So, questions? Does anybody have any questions?
I have kind of questions.
Welcome.
I'm just. Hello, Lucia. Are you hearing me?
Yeah.
Okay. So that's very interesting subject. This kind of it's really a pandemic dark matter because it interacts with something and make this standard model particle becomes dark matter. But in the paper, they do not tell us what type of standard model particles will interact with dark matter. Or,
They actually didn't mention it. They just mentioned standard model particles. That's all.
okay, and they don't give any Lagrangian and any type of specific type of this interaction, right?
Now they just applied this in this final case I show to you, but they don't go through in the details. In this case, I think maybe we will develop this kind of model. I say this is very new. This is from the it's from the 2022. But the author, of course, you know that is this is the creator of Darsusi and is one of the heads of CTA. So I think maybe he want to work with this in the future, but they didn't develop another cases. So that's why I will have to go there and work on it.
So another question is how can you probe this type of pandemic evolution or this exponential growth? Because your final products are two dark matters, basically. So, I mean, usually if we had some kind of annihilation and in the end we have photons or neutrinos, we can explore excess of photons or excess of neutrinos and interpret or put some bounds in our model. In this case, you have two dark matter. So how can we put some constraints on the models derived from this pandemic dark matter, for example? You have an idea?
They actually use, they just mention, for example, that this will be interesting, for example, for the case present that you are using, for example, a decaying dark matter. And of course, this could be constrained by BBN, a CMB. So it's actually pretty easy to do that, to constrain it. In this case, they just use it, for example, for the case of the Higgs, the portal Higgs they are using here. In the interaction of the real scalar of the headband with this coupling here, they use it in order to constrain the CMV. So actually, one thing that he wants to I calculate there is of course the length of the free streaming in order to see that it could be affect, for example, the growth of the galaxies. The development of the galaxies. So of course, if the length streaming is very big, of course it will be constrained. So we will have to publish a paper by saying, oh no, this could above this, for example, this coupling, maybe it is constrained because maybe it will affect, for example, the BVN. Of course, this is a very well measured quantities of the like elements. So actually it's very easy to do that.
Okay. Thank you.
Okay.
More questions? I think that there's no more questions. No? Okay, let's thank Lucia again.
Already didn't put mass. Because here in this computer, I don't know why, but I don't know why the camera is not recognized, as you can see. So sorry for that.
Okay, for the people for looking the stream, thank you for your assistance, and so hope to see you again.
Thumbs up.
Subscribe. Maybe you can donate something. So thank you very much for for coming here, and see you next Friday.
Bye bye.